It is my pleasure to introduce the third speaker of this morning, Valerio Scarani, who is the PI at the Center for Quantum Technologies at the National University of Singapore. And Dr. Scarani will tell us about randomness in quantum phenomena. So please.
Thank you very much. So we already heard something about the interpretation of quantum theory. I'll be much more pragmatical in this talk. I think this is the device to operate. Yes. So first of all, just since we come from afar, some prayers for Singapore, right? This is my research group. Most of them are leaving because they finished their duty. So please spread the voice that I'm looking for people. If you get bored in my talk, you can pray for a group of young people that I'm following in Singapore. That brought them to Rome. That's a flag of Singapore for your information. And of course, we learned this morning in the Mass that we have to pray for another event that is coming up soon. Okay. Now, this talk is not about a few things that we are all very excited about. So it's not about free will and ethics. It's not about chance and providence either. And it's not about randomness as manifested in large human samples, polls, and these kind of things. This is about a very restricted notion of randomness. I prefer to be precise. Oh, by the way, yes. At some point, just to inform some physicists that philosophy exists and Catholic philosophy exists, I wrote a very silly paper on randomness and Aquinas, and I would like to have feedback. I know it's a complete disaster philosophically, this I've already been told. It was meant to reach out to physicists. It was not meant to show that I'm a philosopher. I'm not. But I would like to improve the quality of my philosophy, so I'm sure that pretty much many people here that can read this thing and tell me all my mistakes. Okay, so this talk is about randomness. And I see that the computer in which my slides have been formatted is different from mine, because that should fit in one line, but whatever. So randomness is something where there is a random number generator producing a string of things, right? A string of numbers. And in fact, just to start correctly, there are two possible definitions of randomness, at least. There are quite a few, but and the two are sometimes confused. So let me clarify that point. There is something called process randomness. So process randomness is whether this is a random process. And the measure of this process is unpredictability. Typically, for instance, can I predict the next output of that string given the knowledge of the past? So for process randomness, normally you need to know something about the process, right? If I tell you that, oh, this is a random number generator, probably you will not trust me unless you open it and you see maybe there is something inside that looks like a random process. And most importantly, we need to specify for whom something is unpredictable. Right, this is a question that was brought up to me some time ago by a colleague, Stefanie Wehner, and I am very grateful to her because it's very important. Each time you speak of randomness, especially process randomness, ask yourself, who is the person or the agent, which piece of information do you give to the one that is not going to be able to predict what is going to happen, right? It's a very important question. Random for whom? You come up all the time. And it's necessary for cryptography process randomness, right? If you, well, you'll see it later why. There's notion of product randomness that is sometimes confused with it. And again, this gives rise to all kind of strange debates, which is the question, is that thing the product of the process? Is it a random number? Now, in this case, randomness does not mean necessarily unpredictability, right? Because anyway, it's written there, right? So it's more lack of structure, lack of correlations. And in fact, it's widely conjectured that the proper definition of that thing is not unpredictability, but is algorithmic complexity. So randomness would be measured by a simulator. You build a simulator. What is the shortest algorithm that would produce the same behavior? And well, some people have defined the definition. In practice, it seems that this is well captured by batteries of statistical tests. The NIST, National Institute of Standards and Technology here in the US has the most famous one. So if you have a random number generator, you produce your random numbers, you can send your list to this NIST test and see if it passes. What does it do? It tests whether, whether there are as many zeros and ones, whether all the sequences appear, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 appear all the time. By the way, we humans are very bad random number generators, because it seems that if I start asking you or me to produce a random sequence, we don't produce enough many long sequences of zeros, for instance, right? If I start saying 0, 0, 0, now I feel the need to say 1, right? Because otherwise it's not random, right? And that's how you detect a random number, a human random number generator. It doesn't produce a list of 8 zeros, never, right? So if next time you're asked, just do it, right? Okay, so that thing is sufficient for Monte Carlo simulators and other things, because we don't need really. So usually they come together, right? Usually a random number generator is supposed to produce a random number. But it's important to keep in mind that notions are different, and in fact they are different. For instance, as I just said, a perfectly random process, really random, could produce the string 0, 0, 0, 0, 0, 0, 0 that would not comply. Try to send that one to the NIST. We'll come back immediately saying that's not a random number. But it's a possible outcome. If you tell me, no, my random number generator cannot generate that sequence, then you reduce the entropy, right? Because there are sequences that it cannot generate, so you have some prediction on that. On the other hand, a perfectly random number, that's important for what I'm going to say, can be pre-recorded, right? I have my real random number generator, I generate my random number, I put it on a DVD and I give it to you in a black box, right? And your random number generator, what it's doing is reading from the black box. Now, that's fine for your Monte Carlo simulation. It's not fine for cryptography, because I know your random numbers, right? So the fact that the number looks random, it doesn't mean it's being created by a random. It doesn't mean it's being created on the spot. It doesn't mean that the random process is happening under your eyes. And that's what quantum physics allows you to certify. So let me tell you the end of the story. Quantum physics allows you to certify that random numbers are being created on the spot. They have not been pre-recorded. That's what it means, no locally hidden variables. Okay, but I will come back. Another thing that I will not spend too much time on, but just to let you know that randomness is not just a yes or no, it's a number. Process randomness especially. I told you, the probability of guessing, the adversary has to guess something. So you can get the probability of guessing, which is, well, what do you guess, right? If I tell you that 0 is more probable than 1, you guess 0, right? Because it would be stupid to guess 1. And then you put a log in front of it, because we like logs. It brings powers down to linear things, right? And then you call it mean entropy. Okay, that's the quantifier of randomness. Absolutely standard. I'm telling you, nothing new. Everybody uses that. It's very similar to a Shannon entropy in numerical terms for most distributions. So you can also use the Shannon entropy if you prefer. Examples, for instance, well, the probability of guessing is 1 to the n, so you completely unbiased distribution. Then you have n bits of randomness. The probability of guessing is 1. You have no randomness, right? And last technical thing, because before I go back to more funny stuff, there is a computer science result with a beautiful name of leftover hash lemma, which tells you that you can extract randomness. So if I have that list, and let's say there are more zeros than ones, there are procedures that allow you to extract a shorter list that now looks like a perfect coin, as many zeros and ones and uncorrelated, and the eavesdropper and the adversary doesn't know much. And this procedure extracts exact that number. So there are procedures. So this is a quantifier of randomness, not just because I like it. It has an operational interpretation. It tells you the size by which your string will be shrunk. Okay, that's getting technical, so let's go back to, that's all I have to say about cryptography, right? Cryptography means if I don't know it, it's bad. If you don't know it, it's good for me. Okay, that's the essence of cryptography. Okay, randomness in physics. A super short story. Laplace, famous citation. I wrote it in English because I don't know how many of you speak French. We may regard the present state of the universe as the effect of its past and the cause of its future, an intellect which at a certain moment would know all forces that set nature in motion and all positions of all items in which nature is composed. If this intellect were also vast enough to submit this data to analysis, it would embrace in a single formula the movements and greatest bodies of the universe and those of the tiniest atoms. For such an intellect, randomness for whom? For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Okay, well, that's the famous statement of physical determinism by Laplace in a theory of probabilities, by the way, in the first systematic treatise on probability theory. Now, the 20th century, as you all know, criticized and pointed out those two things. By the way, Laplace was smart enough to notice the second point, which is not completely trivial, that you need computational power, right? And indeed, a lot of phenomena are random, are really random for a being with finite computational power. Deterministic chaos, complex systems. You say, oh, but these are not really random. They are really random for that being. That's the correct definition, right? It's not really random. I don't know also what is reality, like Pyros. Right? Now that's, so just to say that, there is a lot of randomness around. And then, well, this one is quantum physics for everyone in inverted commas, because there is someone, particular God, that does not belong to that everyone, but so that is impossible to know all forces and all positions in the language of Laplace. Of course, nowadays we would say something else. So this is where the 20th century has doubted about physical determinism. Now, a completely different topic I will not touch into, but I mean, it's very interesting also, is to ask whether a chaotic classical system is really random. In a sense, if you want to say, oh, it's sensitive to initial conditions are a real number. How real is a real number? A colleague of mine wrote a paper like that. I mean, do you really believe that there is enough information in the universe to store a real number up to the last digit? Well, if not, then even there is intrinsic randomness also in classical physics. Anyway, let's go to quantum. The quantum claim, okay, right, 1926, before Stephen was saying 1927, I'm not an historian. 1926, by the way, is the same year or 1 year later then Heisenberg and Schrödinger set down the definitive equations for quantum theory. And then Born and Jordan realized that everything is like a Hilbert space, right? So already at the end of that year, after we had the theory, Born came up with a probabilistic interpretation of the wave function. We heard a lot before, and Einstein immediately got mad. The citation I have is 1926, so it must be 1920, well, whatever. And he said that God does not throw dice, right? Then, but this was immediately endorsed by many, so Einstein was sort of marginalized in that matter, and then the probabilistic interpretation became orthodox. 1927, Heisenberg comes out with uncertainty relations, which are correct, and misinterprets them badly in his metaphor of the microscope. For those who believe still in the Heisenberg microscope, come to see me later. Later, 1932, von Neumann tries to come up with a no-go theorem for hidden variables, and the theorem is wrong. Sorry, the theorem is not wrong, obviously. One of the assumptions is completely unjustified. 1935, Einstein, Podolsky, Rosen described their famous non-locality thing, spooky action at a distance, later Einstein called it, and also Schrödinger came up with a metaphor of the cat that we heard before. 1964, that's what I'm going to tell you later, is when John Bell derived this famous argument against local hidden variables. In between 1952, so in between why? Well, because still, with all these things happening, the orthodox interpretation is still probabilistic and so on, and these two groups of people, again, we just heard about them, came up with deterministic variants. So there is a relative state of many-world interpretation and the Bohmian mechanics. It's a bit earlier than Bell. Okay, so the chronology is clear. So let's go to Bell's theorem. Okay, so Bell's theorem is a revolutionary step insofar as it managed to bring down. So Bell was he was trying to do actually was trying to construct a local hidden variable model, and he found out it's impossible. And let me show you what he found out. Of course, I will not show you the original proof of Bell. I will present it in a way that is only 5 years later, and actually in a modern way. And it can be done mathematically rigorous, but I did it in a way that I think high school students should understand. I still don't understand why this is not presented in high schools. So to do Bell's theorem, I need two black boxes instead of one. So I have think of two random number generators. And I need these random number generators, or these black boxes, to have also an input. So it cannot be just something that spits out stuff without any control. I need an input, so there must be some users that can choose between, let's say, two options in my case. Now, importantly, the choice, whatever that thing is, must be random for the black boxes. Well, Eve is not the one that is probably represented in the basilica here. Eve is the typical name for the eavesdropper in our field. Sorry for that. It's not the wife of Adam, right? Although there is a reason. I mean, that's why by assonance it's called like that. So the choice must be random only for the black boxes. Let me give you a very simple example. So of course I put two fingers of humans there, but let me give you a very simple example. I could choose the inputs by taking any book on the table, and if the letter is an even letter, I take 0. If the letter is an odd letter, I take 1. Now, this is not what you would call random by any standard. It has been written many years ago. There is information around the universe about that. However, what matters is that the thing that is in these boxes, the quantum state or whatever, does not know that I'm using that book and could not have predicted that in advance, that I was going to choose with that book. So that's enough of a randomness. We don't need human free will or this kind of stuff, whatever that means, okay? It's enough randomness that whatever is in the boxes is not correlated with the choice of the inputs, okay? So my Alice and my Bob may not be human beings. No need, really. Okay, so let's see. What do I want to test? I want to test, to falsify, the hypothesis that it's pre-recorded. Okay, let me share, some people have asked me how it is to work in Singapore. Okay, let me share an anecdote before that. So in one of my lectures, I did a proof by contradiction, like the one I'm going to do now, right? And then a student came to say me, sorry, Prof, how does this work again? And I was going to this, and I say, well, and now if I do this step, I find a contradiction. And the student told me, well, then don't do it. Okay. So that's pragmatism for you, right? So I'm going to do all the steps and show you the contradiction. So what does pre-recorded mean? Well, pre-recorded means that, again, I can generalize all these things to death if someone is concerned by determinism, whatever. It means that whenever the first button is pushed, there's an instruction inside that says, please output 0. And whenever the second button is pushed, there's an instruction that says, in this case, also output 0. It's okay. And in the other side, 0 or 1. Okay? So that will be pre-recorded. That whenever I push the button, there's inside an instruction in the machine that tells it exactly, is already known what to do in that instance, in every round of the experiment, each time I push. Huh? I will switch to +1 and -1 for convenience of mathematics. It doesn't change anything. Okay, so now I have these, right? Okay, and this is the most mysterious piece of mathematics I'm going to do today. So imagine that these 4 numbers exist. Remember, these 4 numbers are +1 and -1, each of them, or either, right? Let me combine them in that particular sum. And now the claim is that this sum is either +2 or -2. Now this sounds like a very complicated piece of mathematics, but it's not. Because, let me see if I have done it. No, I have not done it. So, okay, imagine that A0 is equal to A1. Then this sum, the last two, see, if A0 is equal to A1, what happens here? A0 is equal to A1. It means that the A0B1 and A1B1 disappear. There's a minus sign, right? So I'm left with A0 plus A1 times B0. Now A0 is equal to A1, so it's 2 or plus or minus 2. B0 is plus or minus 1, so that's plus or minus 2. If A0 is minus A1, we just do the other algebra. Okay? So it's really 1 plus 1 equals 2, 1 minus 1 equals 0. There's nothing more in this equation than saying that if these numbers exist, this value S is either +2 or -2. In every instance, it can be changing according to the round of the experiment, right? Now, well, in every round, you cannot measure this S, because you can only push one button per side. So you can either measure A0, B0, or A0, B1, or A1, B0, or A1, B1. However, if you do it many times, you can measure the average, because the sum of the averages is the average of the sum, right? You can compute your grades per subject or per year, and you get the same average at the end. So that object, the last one, the average of this S, is a measurable, experimentally measurable number. How do I measure it? By pushing sometimes the button 0, 0, sometimes the button 0, 1, sometimes 1, 0, sometimes 1, 1, and organizing the statistics in that way. Okay, now, flash of the obvious, right? So if S can be either +2 or -2 in every round, the average is between -2 and +2, right? Because if you're in university, your grades are between 0 and 6, and a student goes home and tells his parents that he's got 7 in average, you won't believe it. Right? This thing and nothing else is what is called Bell inequality. One of them, Clauser, Hong, Shimoni, Holt, by the name of those who actually wrote that one down. So this is the famous Bell inequality. I don't think we find it very mysterious. And now, well, the argument is simple. If those numbers pre-existed, then this average S must be smaller than 2. If one observes a violation, namely S larger than 2, right, then the assumption that the numbers were pre-recorded as falsified. That's how Bell inequalities falsify locally hidden variables. Oh, but now, what's the relation with randomness? Well, imagine that someone, let's say a human being for the sake of the argument, it doesn't really matter, could have predicted those numbers, right? Then this person could have written those numbers in my boxes. And I would not have seen a violation of Bell inequalities. So again, by contradiction, if I see a violation of Bell inequalities, those numbers are random, right? Because they could not possibly have been known by anybody. Otherwise, this person could have written them in the boxes, and I would have found S smaller than 2. Everything is black box here. There's no photon, there's no atom, there's no measurement, there's no commuting observers, no non-commuting observer, black boxes. Right? This is what we call device-independent characterization, by the way. So, again, the formatting has been changed a little bit. Everything was supposed to be in the red square. But if you see a violation of Bell inequality, you know that the process that you're observing is generating randomness on the spot. As simple as that. Okay, there have been a few experiments going on. So just this is not string theory. Sorry, Juan. It's something that can actually be tested. So how did it go? Well, Bell's theorem in 1964, I told you before. The first tests were done in the United States. They were not conclusive. If I remember correctly, it's either way, either in the East Coast they violate Bell inequality, in the West Coast not, or the opposite. The first clear evidence for violation was in 1982-1983 near Paris, in Orsay, Alain Aspect and coworkers, the famous Aspect experiment. And since then, there have been many more. Yeah, not only with 2 photons, all these experiments, the first experiment were 2 photons, with 2 ions, 2 atoms, more photons, teleportation, and okay. And then there have been these loophole-free tests in 2015. We'll mention them later quickly. Let me just show you. Yes. It's just something we noticed in 2007 and has become a big field in quantum information science, that because this is device independent, you can now certify randomness even quantitatively in a device independent way. So I give you 2 black boxes, I violate Bell inequalities by 2.7, and I can tell you, if that's the case, then I can create 0.8 bits per round really random. So I can compress my string and get, black box. I'll try to do a black box certification of this device that has been a random number generator. You have to open it, check that there is a resistor, there's noise, and so on. This is black box. It's cute, right? You can do quantum cryptography with that. You can certify entanglement, all kind of other stuff. Anyway, that's for research. Now, what kind of experiment is the typical thing? Well, you generate two entangled things, typically photons. That's an example of a source that my colleagues have in Singapore. Incidentally, I'm a theorist, if you've not noticed yet, but I work in a center where there are quite a few experimentalists. That's one of the entangled photon sources we have there. There's a blue laser that hits a crystal that you don't see. And in the crystal, from time to time, one of the blue photons, one of the blue excitations is converted into two red excitations. More or less, the blue is twice the red in frequency. So then these two photons happen to be entangled in many degrees of freedom, polarization, time, energy, and all kind of stuff. And then you send them through some optical fibers, if they are photons. If they are atoms, you do something else, to some measuring locations. What do you do in the measuring locations? For instance, you measure polarization, and your choice that I had before, pushing the two buttons, would correspond to measuring polarization in different bases, right? So you can measure horizontal, vertical, or let's say diagonal, the two diagonal bases. And well, if you do that, you get this violation of Bain inequality. So let me go just show you a few of the historical results. This is the setup as described by Alain Aspect and co-workers. The source was an atomic cascade, so completely different from the one I showed you before. This is kind of like a diamond atomic scheme. We have two ground level, very excited level, two intermediate levels, and then once you excite up there, it can decay into two different paths. If it decays like this, it's first circularly right, then circularly left. If it decays like that, it's circularly left, circularly right. The two possibilities are indistinguishable. They overlap, so create entangled photons. The source was not particularly efficient, to be honest. And there are many open issues there for those who really wanted to go into the details. Why do you want to go into the details? Because the claim that there exists intrinsic randomness in nature is such a strong claim that this experiment has been scrutinized to death. Right? Very, very, very few experiments in science have been scrutinized to the precision of the Bell's experiment. Normally you do an experiment, hey, I measure the magnetic moment of this whatever, and it's 1.5 dBi. And maybe the next group comes and says, oh, it's 1.553. Oh, okay, great, right? Nobody comes and says, oh, okay, fine, right? I mean, why not? These things have been scrutinized because people didn't want to accept the conclusion, right? It's a very strong conclusion, although it's perfectly in tune with quantum theory. So people noticed two things. One is called locality loophole, that the measurements were essentially fixed. So in principle, there could be a conspiracy in which the particles know which, because it's been there for 1 hour, you know, the particles may now know which measurement they're being submitted to. You should change them at random. Again, at random doesn't mean like this. Huh? At random means like this. At every round, right? And then there was something very subtle called the detection loophole. I don't want to enter into that, but it's very simple. It's something like, suppose that you do an exam and you allow the students not to reply to some questions, right? So the student can prepare half of the questions, and then if you ask the question that he or she doesn't like, she can just say, well, sorry, I'm not ready for that. Well, that would be the detection loophole for Bell inequalities. Like if you allow the photons not to reply sometimes, which happens because the detectors have imperfect efficiency, then you could imagine a conspiracy in which the photon, there is a predetermined result, and when the predetermined result is not the right one, the photon just refuses to reply. I can tell you later. And that's the detection loophole. So, which means that to close it, you need to give an outcome on every round, which is possible. Then in 1998, the locality loophole was nicely closed by the group of Anton Zeilinger, back then in Innsbruck, now in Vienna. No, now he's retired, but has been in Vienna for many years. Separation of space, 400 meters. Optical fibers installed under the campus of the Innsbruck University. And this diagram shows something like X is the moment where the Alice device chooses the measurement to perform. And a signal propagating at the speed of light would reach Bob's location after the measurement outcome has been produced. So this is to prove that the choice of measurement of Alice does not influence the outcome that Bob produces. Bob has to produce the outcome before receiving any information from Alice, if anything arrives, because we don't know any mechanism in nature that does that, but if anything would arrive. 2.73 violation. That's the Geneva one. I mean, you're not supposed to know the geography of Geneva, but Cornavin is the train station, and there was a Swiss telecom station there, and my colleagues there went and connected the photon source to the optical fibers. dark fibers, so were not used for the internet at the time. By the way, in 1998, there was not much of an internet, right? Just beginning. So they put the source of photons there, and then they took their bicycle, because they're very ecologists, they don't drive, and they went to Bernay and Bellevue, to two different villages in the countryside, also telecom stations, where the optical fibers hopefully ended, and they put the detectors there. This is the physical distance, and so the physical distance is 10 kilometers between the stations, Alice and Bob, and okay, these are the distances at which they collected the violation of Bell inequalities, sent back the information for processing, and that's the result they got. Well, it should look like a cosine. It does. I can explain to you why it goes down, unlike a cosine. But if you look at the middle, it looks like a very nice cosine, and from that you get 2.4 or 2.7 according to how you treat the data. Again, clear violation of Bell inequalities by photons separated by 10 kilometers. 1998, same as previous. Yeah, since we are here, this experiment was done in University of Maryland, Chris Monroe, a few miles away from here. Certification of randomness using Bell inequalities. One uses your ions. So there are two ions there. There's YB plus, ytterbium plus ions, trapped in that ion trap. And then something, something prepares them in entangled state, and then after that they measure the Bell inequality, and they find, again, 2.4, which gives them 42 random bits extracted. Now, this was not made on purpose, but people noticed the coincidence with the Hitchhiker's Guide to the Galaxy, where 42 is the number that explains the universe, right? Or whatever that is. And finally, okay, these I will just cite them. These are the 3 loophole-free Bell tests. So now with this detection loophole and locality loophole and everything closed, so really no more discussion. The first one done in Delft, and then Vienna and NIST. NIST, this one is the one in Boulder, where the experiment was done. These people come from all over the place, by the way, but the physical experiment was there. Great. Now, I have to tell you something. So what would be the price to pay to save determinism? So for whom these things are not going to be random? Now, not that I want to save determinism, clearly, but I think we have to be honest and say what has been proved and what has not been proved. I had this random for everyone before, was very ambiguous, okay? So let's be a bit more clear, random for whom, or not random for whom. First option, superdeterminism. So that's the idea that there is a single chain of events, and it's a deterministic chain of events. So in this case, that's what I was telling you before, that you have some events can be deterministic that led Alice to push that button. So again, no free will, nothing. Another chain of events that led Bob to push that button, and another chain of events that led to a creation of an entangled pair. As long as these 3 chains of events are separated, or better said, Alice and Bob could be even correlated, but the central one should be uncorrelated from them, then what I said is correct. You certify violation of Bell inequalities, there is randomness. You can even relax it a little bit, honestly. There is something called relaxation of measurement independence. It works, it's amazing. But if everything is correlated, right? If everything comes from a same conspiracy, everything, absolutely everything, well then, also the violation of Bell inequalities come from the same conspiracy. And also what I'm saying, and also what Steve said before, and everything, right? So, well, you have to give up quite a few things, but you can. Of course. Yeah. Option 2, many world. And, well, I've never understood exactly what that means, but again, the many world interpretation predicts that for an agent that is in this world, or in any other, there is randomness. However, an agent that would be able to see all the worlds then would just see this unfolding of the Schrödinger equation that was explained before and would see no randomness at all. In fact, we would see even no events. You would just see this kind of multiplication of possibilities, right? So, but still, even if you're a many world supporter, you still can buy a quantum random number generator and believe that you can fool your adversary here on Earth. Unless you think your adversary has superhuman powers and can see through the whole multiverse. Okay, here I hope you see the power of this random for whom assumption. So even a a many world supporter can buy a random number generator, as long as he or she believes that the person he wants to keep secrecy from is on Earth, as a human being like him or herself. Third option, non-local influences, so faster-than-light communication could restore determinism. How? Well, it's very simple. I told you the results are not pre-established. But it could be possible that maybe the results of Alice are pre-established and the results of Bob depend on receiving some information from Alice. Right? That would be a possibility. It means Bob's results were not pre-established. It does not contradict anything I said, but is deterministic because it's determined by what Alice sends to him. Okay? Bohmian's quantum potential does that job. Well, of course, if you ask faster-than-light communication, normally that's the reaction of most of the audience, right? And I kind of agree. However, we can relax. Even if there is this faster-than-light communication, it could not be used to signal in the past, right? You know that the biggest problem why light is the first signal is because if every user could send a signal at faster than the speed of light in his or her own frame, you could arrange your friend to send you back information to yourself in your past. Trivial general relativity, special relativity, I can show you later if you want. Probably this case, even if there is supercommunication going on, they cannot be done like that. Anyway, what are the problems with this interpretation for me, right? More than the speed of light. First of all, we proved, that's probably my own major contribution to the field alone, let's say, that it must be at infinite speed. And we proved it in a device-independent way, meaning that you can observe some statistics, and if the statistics are observed here on Earth now, you can prove that to explain this with faster-than-light communication, you need infinite speed. Now, infinite speed is a bit disagreeable, right? Even Newton, who had infinite speed of propagation for gravity, didn't like it. A friend of mine showed me that Newton wrote, well, my theory predicts that things change instantaneously and so on. I don't like it, I know how to fix it. And we know how to fix it now for gravity, right? It's Einstein's, but even Newton didn't. So infinite speed means that instantaneously what I do here instantaneously influences the whole universe, right? It's a kind of disagreeable. If you have finite speed, you go into trouble, however, for this phenomenon. Now, the other thing is that, of course, it's very conspiratorial, right? If nature is using a signal, why is it using only for that? Just to violate Bell inequalities and to fake us into believing that there is no signaling, right? If you use a signal, and just use a signal, right? Allow us to signal faster than light. So there is something there that, it must be strongly fine-tuned, not in the sense of anthropic principle. Huh? It must be strongly fine-tuned to use a signal and not to convey any information. I hope I didn't use this microphone for that purpose. I hope I conveyed some information, right? Okay, so conclusion. Well, the conclusion is in big, right? There is identifiable randomness in physical phenomena, but there is a preliminary and a conclusion, right? So as soon as a suitable chain of events are independent, though possibly deterministic, again, I don't need to postulate any prior randomness or to postulate even free will anything, but just independence of causal chains and lack of correlation of the choice of the measurements and of the creation of the state. There is a random for a being that does not perceive the multiverse, that cannot read the Bohmian potential. Bohmian potential in principle cannot be read, but imagine a being that can read the Bohmian potential, if it's there, a being that cannot read the superluminal influences. So even if you uphold one of these deterministic interpretations, I think very few people here in this room, but sometimes it happens, still, there is certifiable randomness in physical phenomena, let's put it like that, in this universe, and for a normal being. And that's the end. Thank you very much.
I'll be brave and excuse the simplicity of this question. What if I want to win the lottery?
If you want to wake up?
The lottery.
Then you need to predict something. Then you better make sure that the lottery is not using a quantum process. In fact, some colleagues of mine that commercialize quantum random number generators, not of this type, they need to be characterized. Their main client is online casinos that can thus claim, of course unjustifiably, that unverifiably, that they're using real randomness in order to draw their things, right? So that they're not cheating. Of course, you have to trust them that they're using real randomness, right? So somehow it's a little bit of a, but yeah, my colleagues who sell quantum random number generators, in Singapore, we have not managed to get grants from the local casino to do these experiments.
I have a question. Entanglement, could that be also observed in other than physical measurements, such as biological? And also, is special relativity in question now? And or is that still because of the idea of superliminal speed? Are we now questioning the special relativity, the whole idea of the postulates?
Okay, for special relativity, you can turn your head to your left 2 persons and you ask Juan, the person there, he knows much more. What I can tell you is that in quantum theory, we are not questioning special relativity as much as they are in cosmology. Strangely enough, cosmology, they like to do all kind of double special relativity and all kind of other theories that I'm not familiar with, but they're much more cool about that than we are allowed to be. If a quantum theorist like me criticizes special relativity, he gets immediately hammered by obvious incompetence, right? Because I know my special relativity by undergraduate courses. But those people who are really working on those fields have no qualms whatsoever in exploring with that. That's for the second question. For the first question of entanglement, you know, why my finger does not penetrate this building is according to current quantum theory, is because the spins of my electrons here and the spins of my electron there, there are only 2 possible spins, right? And my electron trying to penetrate here at some point finds an electron in the same state, and it says, sorry, thank you, but this state is already occupied. And that's due to entanglement, right? I can only put, I mean, in the sense entanglement, because you can put 2, you can do a single state, right? And then, so if you want, if you take quantum theory as a correct, fully correct description, which may have some problems, entanglement is everywhere. It's the fact that we are standing here instead of, you know, just hanging around. I mean, our molecules are, everything is entangled at the end of the day. As soon as there are 2 spins in the same orbital of a molecule, that's an entangled state, right? It's not this one is up and this one is down. That's a single state, because it's not up and down in some direction. It's opposite in every direction. So the question is not so much if there is entanglement. The question is whether you can extract or use or see manifestations of that entanglement. And the answer to that one is, so far we haven't. But I won't exclude it.
Thank you. Thank you.
Hi, thank you for your great talk. It was really fun to hear about Bell's inequality. I wanted to build off of the previous question on entanglement. In your talk, if I understood you correctly, you said that faster than light propagation of information is impossible. Is that right?
My name appears in a crackpot website. Well, I hope the person is not in the room, by the way. I forgot the name. Of alternative scientists, and Valerio Scarani believes in superluminal communication. And let me clarify, I don't believe in superluminal communication. So what I'm saying is that if you want to recover determinism, the only option in normal physics, I would say, so without going to superdeterminism, to many world, so let's put it like this, you can recover determinism in this universe without multiplying the universes, without going to epistemology, only by adding superluminal communication. Right? That's all I can say.
So maybe I don't understand entanglement right. So
neither do I. Yes.
If I'm I'm going to borrow an analogy from the author David Griffiths. Imagine if I have 2 Frisbees and I suddenly get caught in an opaque cloud of fog. and I throw out the frisbees, and you're not allowed to observe the direction one frisbee is spinning in, until they get about 1 light year away. And then you observe that one frisbee is spinning clockwise, and that automatically means that the frisbee...
There's nothing strange in what you're saying.
Yes. So does that... So when the wave function a light year away gets collapsed to being a or the opposite spinning frisbee, are you... I don't think any massive particle moves faster than the speed of light. But how do, if I may, I just would like for your remarks to square that with the fact that there's not superluminal propagation of information. Sorry, it's open-ended, but I'm interested in your comments.
It is correct that any mechanism, not classical, not quantum, any mechanism that would explain these correlations requires transmission of information. There's no discussion about that. That's the power of Bell theorem. You can't get away with randomness. You can't get away with wording like, I don't uphold realism. So yes, any way if you want to ask the question how nature does it, the answer is, the only possible answer is through a form of communication. Now, whether it is superluminal communication in our 3+1 dimensional space-time, or it is something in one of the 25 other dimensions the string theorists, or sorry, how many are there? A few, no? You know, if there is a fifth dimension, maybe two entangled particles are always close to each other, and the communication goes on through that channel, and then what's the problem, right? So what I mean is that, unfortunately, these kind of models have not led to any, how to say, interesting prediction. It's like Bohmian mechanics, right? You can say, oh, it's deterministic. Bohmian mechanics does the trick, by the way, right? The quantum potential, if you change something here, it changes instantaneously or the whole universe. Fine. It's just that the prediction of this, so there's nothing that you can test yet. Maybe the day when we know more about dark matter or dark energy or whatever, maybe there is something maybe something will explain, right? At the end of the day, we don't know, right? But what you say is true, that I can't get away, if you want physics to answer the question how nature does it, you can't get away without communication. And then you can go into instrumentalism and say, the only task of physics is to give me a theory that predicts the right things, right? And don't ask that question, otherwise we go into trouble. Most of my colleagues would adopt that posture. I am still agnostic in that matter.
Thank you so much.
Welcome.
So thanks, Valerio, for your talk. My question is superdeterminism still falsifiable? Is scientific? Because...
No.
Yeah.
No.
So you could still say that if you go back in time...
Oh yeah, everything comes from the Big Bang, and then the Big Bang might have decided that everything was written there, yes.
And are you aware of these experiments, I think, that by Seilinger's group, that decisions are taken from light coming from
yes,
stars?
I find him very weak.
Could you comment on that?
Yes, very simple. Okay, so he's referring to experiments where the setting of the random numbers, these things that Alice and Bob are pushing, are detected by pointing telescopes to very different stellar objects and getting the light from the fluctuations of light from them. The idea being that now if these things have been correlated with the source, they would have been correlated essentially before inflation or just after inflation. I don't remember exactly when. Okay, so why I find it rather weak? Because who are we trying to convince? Right? Physicists have been convinced that Bell inequalities are violated since Aspect. Now, suppose I want to convince a person that I would define as a crackpot, just for simplicity of the argument. This person comes into my room, and I show to him, crackpots are men most of the time, so I can avoid inclusive language in this case, that I show to him that I'm choosing the settings of my Bell test by, I go there, just go there, take a book. Now, this guy has to believe that the content of the book is correlated with the source of entangled photons. He can, he's a crackpot, right? But, contrary, the guy goes into Zeilinger's lab and sees huge telescopes allegedly pointing towards the end of the universe, and they tell you, no, we are detecting light from that star and so on. The guy can just say, you're cheating me. Inside of this telescope, there is already something you've written. It's not a telescope. So to convince a crackpot, that thing is completely pointless. It's amazing from the point of view of physics. Yes, it's nice. I would have supported publication if I had been the referee. In this case, I was not. But yeah, great. I cite it in my book, by the way, because I have to cite it. But in forthcoming, don't look for my book. It doesn't exist yet. But yeah, I do. So sometimes you have to think, who am I trying to convince? Right? And if you want to convince the crackpot, I think that the Geneva phone book argument, the one or whatever, is much more convincing. I mean, if someone goes, no, I really believe that the book written by Professor Fraser is correlated with my source of photons, you know, I will not discuss with that guy anymore, right? That's it. That's the end of the story.
Well, I have a question about the speed of gravity. You mentioned it in your talk about it being infinite, and Tom Van Flandern, he's a nice Catholic physicist, Jesuit product, has a paper on that. And of course, Tom passed away maybe 5 or 10 years ago. Is there anything new on the speed of gravity?
Not that I know, but again, many other people in this, I'm really doing this kind of non-gravitational stuff, so I'm not following at all those debates, I'm sorry. I'm not the right person to, other people may come to you if they know something and answer this question.
Yeah, the issue is, of course, the gravity points at where the actual planet is. It's not where it was, you know, the time delay to go. And
again,
because if it happened, then the whole universe.
Yeah, from time to time, people tell me that there are some orbits that cannot be predicted by Newton and whatever, and I just take it as an interesting piece of information. And unfortunately, there are so many interesting things in life that you cannot do, and that's one of them, as far as I'm concerned. But I'm sure some people in the room know better than this, and you can just address.
Okay, thank you very much.
Welcome.